We're now ready to see what actually happens in network exchange experiments. And remember quickly, the way these experiments work is the experimenter recruits usually a small group of people into the lab. The people play the role of nodes in the social network that the experimenter's created. Two nodes can exchange if they have a link between them, as they can be matched if they want. If they exchange, they get 1 unit of surplus to divide between themselves. Anyone who's not part of any exchange gets nothing. Everyone can be part of at most one exchange. And then this is repeated, and we see what happens after a long period of time. These experiments have been run many times, and we're going to look at a bunch of examples. First, let's start with the simplest example, which we'll call a two-node path. We have two nodes A and B, which have a link between them. So they can, if they choose, be matched up. If they're matched up, they generate a surplus of 1. Typically what happens in the lab is that A and B actually do agree to being matched up and split the surplus. Now that surplus could be split in any way between A and B, all the way from A getting nothing to A getting everything, and B then correspondingly getting nothing. But what typically happens is you get what looks like a fair exchange, with A and B on average each getting about half. That one's pretty straightforward. Let's look at a three-node path where we have A, B, and C with links between A and B and C. Okay. Now, in this case, even though there are 3 nodes, there can only be 2 of them matched up. So we can get a matching, but not a perfect matching, because we can't match all the nodes. We have an odd number. Typically, an exchange here takes place between B and either A or C. B, of course, is in a powerful position. B tends to get most of the surplus, but not actually all of it. So for example, when A and B get matched up, B tends to get around 5/6 of the surplus, and A gets 1/6, and C gets nothing. So B doesn't end up with everything, probably because no one is willing to be taken advantage of completely, right? Why would A be willing to be in the exchange at all if he gets actually nothing? B has to give him a little bit. And he can give a little bit to either A or C and be part of that exchange. That one too is pretty straightforward, except for the details about exactly how little does B's partner get. Let's look at something slightly more complicated, a 4-node path. Okay. Now, in this path, B and C have power over A and D respectively. But let's think about B versus A. B looks more powerful than A, and the experiments reveal that, but B's power is limited because B's potential partner, in addition to A, that is if he decides not to trade with A, is C, and C too is powerful because C has D as an alternative. So what you typically see here is 2 exchanges between A and B and between C and D, and B and C get more than either A or D because they do have some alternatives, so they get more than a half, but what they get is not close to 1. They are more powerful, but not completely powerful. Let's look next at a slightly more complicated example, just extending our path with one more node. Now A, B, C, D, and E. From the 4-node path, you might have thought that being in the middle of the network was more valuable, right? Previously, B and C in that 4-node path had power because they were inside the network and had alternatives. Well, here, C is in the middle of this social network, but in fact, what the experiments reveal is that C is very weak. In fact, C is almost as weak as A or E, and B and D are now very strong. Typically, what you see here is exchanges between A and B and D and E, with C being excluded. A, B typically exchange with each other, and in this case, B gets most of the surplus, as does D in his exchange with E. That's what the experiments reveal. Not all of it typically, because again, why would A or E trade if there's no surplus for them? But B and D get most of it. C typically is involved in no exchange and gets nothing. That's happening here, it seems, because C's partners, potential partners, are B and D, both of whom are very powerful. They have the ability to exploit the relationships with A and E, and that leaves C with nothing to do. Let's look at one last example of this, a triangle. This time with a triangle of A, B, and C, where A can trade with B or C and so on, there can only be one exchange, right? Think about this as best friends. If A and B are best friends, C is excluded. If C and B are best friends, A is excluded. Imagine any exchange that might occur. Let's say, for example, between A and B. That exchange generates a surplus for A and B, which they share somehow. But in that exchange, C got excluded. If C is excluded, C is getting 0, and C has an incentive to go to A and B, particularly the one who got the lower value in the exchange, and offer them more. So suppose, for example, that A got a fourth and B got 3/4. Then C could go to either of them actually and offer them a better deal because C got nothing. But C might go to A and say, I'll give you a half if you'll join with me. And then we might have A and C exchange next time. But now B is excluded, and B would be tempted to go to either A or C and offer them a better deal, and so on. What happens in this triangle typically is that things are unstable. Unlike all the previous examples, this one does not settle down. It tends to bounce back and forth with various people being paired up. Okay. Now with those experiments, we have some idea what happens in networks, and we want to try next to build a theory to explain the experiments, but more importantly, that we can use more generally for social networks that are more complex, hard to write down or hard to run experiments on. And that'll be our next topic.